I'm Tim Ventura, and we're joined today by Dr. Robert Sutor, a quantum computing subject matter expert, Vice President and Chief Quantum Advocate at ColdQuanta, and author of Dancing with Qubits, which follows the publication of several previous computer science-related books. Dr. Sutor has a BA in mathematics from Harvard and both an MA and PhD in mathematics from Princeton University. His career includes over 40 years of technology expertise, including over 2 decades of senior leadership positions at IBM. So Bob, welcome, sir. It is truly an honor to be able to interview you on quantum computing. But before we get into this topic too deeply, I want to start out with your book. What is Dancing with Qubits all about? Who's it written for? And what inspired you to write it?
Well, let me start with the last question. What inspired me? I am a mathematician by training. I have a PhD, as you mentioned, but it was really only 7 or 8 years ago that I started getting involved in quantum computing, and indeed it was at IBM Research. So you can imagine IBM Research headquarters, very large building, 1,100 people. I'm in the math department down at one end. All these physicists are down at the other end. I don't know what they're doing, really, but through some reorganization, I started hearing more and more that they were working on a quantum computer. And it was intriguing. I think I, like many people, had heard this word quantum years ago in the Quantum Leap, or movies like Ant-Man and the Wasp and the Quantum Realm. And it's one of these terms that people just want to know what you're talking about. But anyway, I started to get involved with this, and I realized that I came from a physical background. But because it's computing, you got to program it at some point. So I started learning about it and discovered, in fact, there was an awful lot of math. So I figured I should be able to learn the math. I should be able to figure out what's going on. At which point, I discovered that the materials to learn about quantum computing tended to assume you had about 4 years worth of physics. I didn't want to. I have learned a lot of physics, but I'm a mathematician and not a physicist, but specifically and on purpose here. So as I started assembling this knowledge of learning for myself and realizing that there were these gaps that you had to keep jumping to this place and that place and whatever, I decided to write a book. And I decided to write a book for someone who came from my type of background, which was math or computers. I wanted to make it a smooth narrative from beginning to end. None of this stuff like, as everyone knows, and then they throw out some equation that nobody almost knows, right? And things like this. And so that was really the genesis of the idea of Dancing with Qubits and how I ultimately executed it.
Okay. Now, again, for the audience sake, and I will put links in the show notes for this, but this isn't your first book. You've written computer science books on Python, LaTEX, and Axiom. And so these are basically programming guides. So I'm wondering, could you tell me what it was like to switch the focus from stuff that is so concrete, I guess, in some ways, to a book on quantum computing?
Well, so the sequence was, and here you actually have to jump back 30 years to when I wrote a book about computer algebra. So people are familiar with systems like Mathematica and Maple, systems that manipulate polynomials and matrices as opposed to like Excel that are very numeric. I wrote that book. I wrote a book about formatting mathematics again in the 90s, and then I got busy. I went over on the business side of IBM, came back, then I wrote Dancing with Qubits, and then I wrote the Python book.
Okay.
And so Qubits was very much for anyone who I thought really liked math, but started with a high school math education. I would bring you from that point to everything you needed to know to understand the basic algorithms of quantum computing. Dancing with Python, which was the follow-on book, was saying, well, many people learn Python as a basic programming language. It's a great language. It teaches you all the basics. It's a very modern language. What if I try to throw in some quantum computing elements to this as well? So instead of learning all the classical stuff, strings and lists and numbers and things like this, and then learning quantum, could I interweave them? Because, if you're just starting, I started coding when I was 15. I have a lot of classical computing baggage in my head, right? So you have to almost unlearn some things for quantum. So this book was an attempt to, in a very homogeneous way, blend classical and quantum computing. So it's kind of a 1-2, dancing with qubits, which is the theory, the math, dancing with Python, basic programming with quantum computing.
Ah, okay. Now you mentioned getting busy with work, and I would say that's an understatement. Again, 20 years in VP level roles, right, at IBM, and you've just recently come on board with ColdQuanta, and you're also in a senior leadership role there. So ColdQuanta builds and integrates quantum computers, sensors, and networks. So let me ask about how your experience at quantum computing with IBM went and what inspired you to make that jump to ColdQuanta.
Well, I think to begin with, it shocks a lot of people to think that anyone could be at one company for 39 years. And you do have to remember IBM is a large company. At its peak while I was there, it was probably over 400 people. So you can have lots of different careers and stay in the same company, have the same payroll, the same healthcare and these sorts of things. And it suited me just fine. I worked out of New York State in different ways, had many different roles, technology and business as well. So I did get involved with quantum computing over the last 5 or 6 years of my career at IBM. Clearly, this is a type of computing that will keep us busy, not just for the next few years, but for the next few decades and
absolutely, yeah,
maybe centuries for all we know, right? So we're in the first few years here, and I felt it was a great experience at IBM with IBM Quantum, but it's building computers a very particular way, so-called superconducting qubits. These are chips. They're not pure semiconductors like you might have for the memory or the processors in your laptop or your phone. There are some analog aspects to this that actually give you, if you will, a quantumness. But to me, I felt after going through several generations of this, and they made great progress, I felt, I'd like to learn a little more about this. Are there other ways of making quantum computers? What are the other applications for just this quantum stuff? In fact, one that, as I was learning about this, if you've ever had an MRI or have a friend who's had like a shoulder problem or a knee problem and they get an MRI, that is quantum. That's a quantum application. It's a very high resolution image that's safer than X-rays. And oh, by the way, it goes back to the 1940s. So we've been using quantum technology in that way, as well as things like quantum atomic clocks for years and years and years. Yet, it's only this quantum computing stuff that gets all the attention. So for me, really 2 sides with ColdQuanta. Well, 3, let me say. 1, time for something completely different at this point in my career. 2, let's look at another way of building quantum computers and maybe, in fact, making small but powerful quantum computers that can fit at the edge. So not just big quantum computers and big data centers. As we all know, pick up your phone, you got a supercomputer in your hand, compared to what we had years ago. But then there's quantum sensing, quantum inertial sensing, gyroscopes, atomic clocks, radio frequency receivers. There's this whole breadth of other things to do. And with ColdQuanta, you can use the same technology, the so-called cold or neutral atom technology, to give you the quantum elements of how you implement these.
Ah, okay. Well, and one of the things that you touched on is what's being called quantum 2.0 or the quantum revolution. You'd mentioned that a lot of these technologies, MRIs, for instance, have been around since the 40s. It seems like a lot of these, the physical principles for this date back to the 20s, right? I think that was when the physics really started to get busy. And and the technologies for it date back in many cases as well. Quantum computing itself, they were writing about this 20 years ago. It seems like it's the convergence that's creating a paradigm shift. And that's one of the things that's truly interesting about this to me. is just seeing it progress forward and move to the next level, I guess, as a specific set of technologies rather than this diverse collection of bits and pieces that has been in the past.
Well, you mentioned the 1920s, and there were lots of very famous names like Heisenberg and Schrodinger, and in fact Einstein. Quantum mechanics, which is the model in physics of which in space, was very controversial, very, very different. I think a lot of people are familiar with Einstein's work at the beginning of the last century, relativity, and how it upended really the Newtonian way of looking at it, because Einstein really looked at the very large, the effects of gravity, the effects of traveling near the speed of light and things like that. Well, that's the very big, but there are also a theory of the very small, and that's quantum mechanics. And that was stranger than anyone could possibly imagine. Einstein hated it, absolutely hated it, because he believed in this very real deterministic universe. One step follows another always, and you could always figure out where you're going to end up. Well, it turns out that quantum mechanics brings in probability. The universe actually is not deterministic. There's a chance of this will happen or that will happen. So not only do you have to account for this in the math and the physics, wow, I mean, it's philosophy. Why does this stuff work, right? So we get the Copenhagen interpretation and the many worlds interpretation. Every time there's a choice to be made, the universe splits and things like this, and it's fascinating stuff. So a lot of people thought about this. They developed the physics. It helped them to understand chemistry, of course, light, many things like this. And then, as you pointed out, in the early 80s, people started saying, nature isn't a bunch of zeros and ones. Nature isn't like these classical computers we've been doing since the 40s. Nature is actually ruled by quantum mechanics, it appears. If you could build a computer that operated the way nature works, maybe we could compute with these things a little better. Maybe we could do the chemistry in a computer instead of in the lab. Maybe these problems that depend on probability, optimization problems, or even, in fact, some very hard computational problems for AI. Maybe we could do these much more efficiently. So this started off people beginning to think of algorithms. But it was all hypothetical. If one had a quantum computer, which we don't, you can do this. But they got amazing results like Shor's algorithm. And I know you want to talk about crypto. We can get back to that. But it was only to really the end of the last century and in the last 20 years or so that people start to build quantum computers. They're small, but that's what's triggered it. We can build them now.
Well, again, this area is just surging forward, and the quantum computers are definitely what's driving that. So now ColdQuanta is one of several startups that are emerging in the quantum tech space. And so one of the things I wanted to ask was, is this the beginning of a gold rush for quantum computing like we saw back in the dot-com era? Do you think that we'll see a situation in the future where investors are just throwing anything with money, throwing money at anything that uses qubits? And is there the risk that we may end up with over speculation again, like we saw during the dot-com boom?
I don't think we're in that period right now. In fact, I would almost argue we are in the period after the dot-com bust, which was around that busted around 2001, 2002. And yeah, we had 14 different online pet stores, right, that had multi-billion-dollar valuations and silly things like that. I do think we are seeing generations. I think if you will, if you follow this, the household names associated with maybe superconducting, so-called ion traps, different types of doing quantum computers, that's the first generation. And they've made modest progress. But really, when we talk about qubits, someone may say, hey, look, I have this great computer with a few dozen. I have this 100 or a few hundred. All great. But we need 50,000. So I applaud your progress. You're making good progress, but you have like 100th, 1,000th the number of qubits we're going to need to do anything really useful. So we're in this period where people are buckling down a little bit. You're
Okay.
seeing cold atoms, a few other of what we call modalities, ways of representing qubits come in. A little bit less noise about this. Yeah, there are a few startups, but frankly, a lot of them are pretty small. They don't come out with billion-dollar valuations. There's often spin-outs of academic departments. So what I meant about after the dot-com bust, so imagine this, 2002, everybody's exhausted, the end of irrational exuberance, right? That was a term that people used. And then we all just kind of buckled down. And then, people kept working, but on the serious projects, on the right dimensions. By 2007, in fact, in quantum computing, we had the development of what was called transmon qubits, superconducting qubits. And that was the birth of what Google's doing, what IBM's doing, what Amazon's doing, and other people like that. The iPhone was introduced in 2007. Deep learning, part of AI, really hit its stride in 2007. So these quiet 5 years, when people put their heads down and really said, let's forget all this stuff about startups and investments and unicorns and things like this. I think that's where we are now, that people are really buckling down, experimenting with what technologies will work. Let me also say, in this quantum world, there's not going to be one winner. That's silly. People like to pick winners. They think it's a horse race of some sort. It's not going to be like that. Some of these quantum technologies will work great for big machines and data centers. Others that people think will be great for quantum computing may not pan out that way, but they'll be great for quantum memory, right? So it's going to be an interesting mix of which technologies are good for what and how they work together.
Yeah, absolutely. Now for me, and I'm too young to remember the 1970s, but it reminds me, in this era that we're in right now, reminds me a bit of what I've read about computing in the 70s, where they had an idea where it could go. This was, I'm thinking back before Apple Computer, back before Microsoft, and they didn't realize exactly how big it would get, and they didn't really have that killer app yet, right? And maybe I'm thinking that because, for the most part, these quantum computers they're still in specialized data centers. They're very much test machines. As you mentioned, the qubit levels are nowhere near the 50,000 or more required for complex calculations. It's almost like the punch card era for quantum computing in some ways. That's kind of what it reminds me of. And of course, many people are going to look at that and say, well, yeah, there's potential here, but where could this go? Well, they have to keep in mind that those punch cards are the supercomputers that are in our pockets today. It's the same thing. In fact, those are Linux-based machines, so it's almost exactly the same thing. It's just much more modern. So
people sometimes ask me something along the lines of, well, if the modern computing era began in the 1940s, and actually, a lot of this stuff came out of World War II, right?
yeah.
And what was done there. And then after the war, it was declassified and commercialized in the 1950s. They want to say, well, where are we in quantum relative to that? Are we in the 1950s, right? Or as you pointed out, punch cards went well into the 70s. And yeah, we're definitely in the early stages. There's no question about that. Except we have 80 years worth of knowledge. Programming languages, it's not like we're like, hey, what is a programming language? Let's try to make one.
Yes. Yeah.
Years, right?
And I think that's an incredibly important point, is we have the infrastructure in place for these technologies. And so it won't be 1970s to 2007. It may be more like 1970s to 1980, right? The next 5 to 10 years, we may see that kind of movement here. And it's because all of these other pieces are in place to bring this forward. And the need is there also, right? It's not like, there may be room in the market for, one personal computer. I think that was a quote back in the day. Now we know where the need is for this, right? And we know that there's probably going to be a much greater need than ever before in the past. We're just not sure exactly where that is yet. That's kind of the impression I've had.
Yeah, the word I like to think about is how do we integrate quantum computing with classical? I don't like the phrase hybrid because computing is always introducing new technologies, like GPUs, right? So GPUs were originally, as the name, graphics processing units. They are classical processors, but they're highly specialized for things like matrices, right? And geometry, which is if you're doing a video game, that's what it's about having things move around on the screen. And then somebody said, hey, we do a lot of the same sort of math in AI. And so now, arguably, the biggest market is for these GPUs in AI applications. We'll forget about Bitcoin for the moment. They seem to like them too. But so that is, computing evolves and absorbs.
Yeah.
So hybrid kind of says, well, it's something completely different. And then, so this integration, if you talk to a client, let's say a financial services company, they don't want to hear, hey, here's this new technology, rip out everything you've got and plug this in. And they say, well, how much is that going to cost? Is it going to work? Do I have people trained and things like that? Instead, they say, look, these are the types of things I do. This is the workflow. This is how the data moves through the systems. These are my choke points. Can quantum help speed up over here, over there? And yes, we will get knowledge. Maybe we will replace some processes, but it's this integration that's essential. And that's driving a lot of what algorithms do we work on, right? And it will drive where a quantum computer is actually used and by whom.
Yeah, absolutely. Well, a good example of that is the Apple A series chips, right? And this is kind of close to my heart because I've seen this evolution from the relatively basic ARM processor, which was invented in the early 80s. Now the mobile environment pressures have led to you have neural networks built onto the chip. You have cryptographic processors built onto the chip, and in the case of the neural network, those function very differently than traditional silicon does, but it's not something that we think about, right? As you mentioned, it goes into the workflow. It's like, I have this task that needs to be completed. Can this technology do it more effectively? So, in some ways, maybe quantum computing will take on that role, I guess. You'd mentioned AI applications. Do you think that we'll end up seeing this someday in GPUs?
Probably, well, instead of GPUs, alongside GPUs, maybe. So the type of math that's involved with quantum computing is somewhat similar to the type of math done by GPUs. There are some differences in the way it computes, but when you look at AI applications, one place that's easy to sort of say is, well, how do we do the different things in AI, like machine learning or deep learning today, right? So let's not get fancy with all this extra stuff. How do you do it today? What's the math? What are you computing? Well, okay, what processors help me do that faster? So in some cases, it's GPUs.
Okay.
In other cases, we may say, okay, this quantum computer will help me do that type of math faster. So do what we're doing today, just do the math faster, right? Now, if that was the end of the story, it was sort of like, okay, you gotta have a super AI machine and that's lovely. But in fact, there are elements of quantum computing and indeed quantum mechanics like entanglement, where two different particles or two qubits can get so tightly correlated, we can no longer think of them as independent, right?
Yeah.
Strange concept. This was the spooky action at a distance that Einstein hated and things like this. But nevertheless, the point of entanglement, which is beautiful mathematically, but it has no counterpart classically. So I'm giving you this amazing structure and tool that we can't do. So I would argue, if you can't find new types of patterns with this weird new thing, right, for AI, then you're not trying hard enough. So quantum will help us do what we did before, but faster, we hope. but it will give us new tools to do this pattern matching, to do whether it's neural networks, whether it's classification or anything else, to allow us to do it in different ways. And that's where I think the breakthroughs will come.
Yeah, yeah. Well, if it's okay, I'd like to touch on what IBM has been doing recently. And the reason is they've just made headlines yet again. So in December 2020, a group at UTSC claimed quantum supremacy with a 76 qubit computer, and that's only 2 years ago. In November 2021, IBM presented Eagle with 127 qubits. Just last week, they unveiled Osprey with 433 qubits, and they have plans next year for the 1,121 qubit Condor system. And so this performance is just increasing massively. And as you mentioned, we will probably need to get to 50,000 or more. So it's definitely not there yet, right? Again, harkening back to the 1970s, it's like seeing those, those initial 8-bit systems become 16-bit systems, and then you get into the, the 1980s, and you're into 32-bit systems, things like that. But seeing this massive jump in performance every year, it makes me wonder, what does this mean in terms of computing power and performance? Where do we see these things going, do you think?
So let me first change one word, which was performance. I could have a really expensive big car, and it could be slow as molasses. That is, bigness doesn't give you performance, right? In the case of qubits, having a lot of qubits is good, but if they're really bad qubits, if they have a lot of errors in them, you're not getting good performance. You can't compute things because there's so many errors in the system. And so typically with quantum computing, you have to go down at least another level. You have to look at a few other terms. What you talked about was what we call scale, which was number of qubits. And yes, absolutely. You can't solve big problems with a few qubits. You need a lot of qubits. So that's table stakes. But now we have to talk about things like the speed. We have to talk about the connectivity. So earlier I mentioned this notion of entanglement. You have to actually somehow connect qubits together in different ways, right? Can I connect this qubit to this one, that one, or am I limited? Because if I can't connect to lots of other ones, I have to do all these extra operations, and that slows me down. And there's this technical thing called coherence time. Qubits, it's not like your laptop where you put information in and then you come back a week later and it's still there. Qubits become chaotic. The information in them starts to just kind of wander away. Here's an example. Let me say it this way. Let's say I give you a photo.
Okay.
Every second, and today's photos have millions of pixels, millions of dots in them. But here's the thing. I'm going to give you this photo, and every second, 1,000 random pixels will just turn black. So I'm looking at the photo. I know who it is. It's a photo of you. Yeah, okay, that's me, if you're thinking. After about a minute, you can start noticing this thing's getting a little fuzzy. And after an hour, you can say, well, I can sort of still make out that's me, but I can't figure out what the posters behind you are anymore. So I can still glean some information. Well, qubits do the same thing, actual physical qubits. They have certain values or states, and then those states start to wander. There's only so much time you have to work with them. So the connectivity, if you have to do all these extra operations, you can't do the math you want to do because, right, you're racing against the time. So with quantum, it's not just the number of qubits. It's all these other interesting factors. Now, there's one other thing that almost nobody talks about. And I do want to make this clear. So we talked about this need for what I call, let's say, 500,000 qubits. If I give you a chip or a cold atom array or an ion trap or something that has 1,000 qubits, and that's the maximum number you can stick in there, 1,000. You just can't make a bigger chip or array or anything else. how are you going to get to 500,000 if the biggest thing you can make has 1,000 in it? We got a problem. We've hit a wall. You can't squeeze any more qubits in there. Well, what you got to do is you have to connect. You have to actually connect these quantum cores. And this goes back to when you were talking about classical chips. Around 2005, Intel and AMD introduced dual core processors.
Okay.
Before that, every PC, every Apple PC, IBM PC, compact and things, in the processor, there was just one brain. And then as Moore's law started to slow down, they said, well, hey, we're going to throw in more processors. So it was 2 back then. I think the new iPhone has 6. I just got a new laptop. It has 12. There are supercomputers that have thousands of them. We have to do the same thing with quantum. We have to have separate quantum chips or arrays or traps or something and start connecting them in quantum ways. Not with just little wires, but in quantum ways. We don't know how to do that very well. So in addition to this notion of how do we build qubits and these cores, this connectivity and networking is going to be absolutely critical over the next few years. And that's one of the exciting things we'll see.
Now, as this performance continues to increase, and again, my apologies for using that word, but will we reach a point where quantum computers will stop being used for general computing activities, or do you think they'll always be limited to specialized computing roles? I'm wondering if we'll ever see, are we ever going to see a desktop quantum computer, or will it always remain something like a math coprocessor, for example?
I think eventually you will see rack-mounted quantum computers. You won't see them for the types of systems that require massive refrigeration. Some of these modalities, as I referred to it, ions or cold atoms, you need a little bit of refrigeration. But instead of taking up a room for these freezers, it will be something that can kind of fit in the palm of your hand. And it's related to getting a better vacuum and performance of the qubits within that vacuum. So something that fits in the palm of your hand is still a reasonable thing to expect to do in a rack. We are going to need to see big improvements in photonic integrated circuits. So right now, when you think of, open up your PC, look at the motherboard. Well, what flows through all those things are electrons.
Yeah.
Well, photonics or photons are light. And so we're going to replace the bigger and bulkier lasers that we now use for some of these other types of systems with smaller units, right? So you can kind of imagine ultimately it's kind of a biggish chip, but still manageable. Luckily, we don't have to rely on the quantum computing or the general quantum sensor technology industry to do this, because we're not the only ones who use lasers, right? Blu-ray, right? Every time you scan something at the grocery store, if you've had eye surgery, there's the whole laser technology industry is billions and billions of dollars with so many applications. So in parallel to the development of the quantum technologies, we will see this driving the cost down and driving the size down of the photonic and the laser components. And that will ultimately yield smaller quantum computers and other quantum devices. Maybe not a phone, maybe not a laptop, but something you can throw in a rack someplace or stick in a satellite, maybe.
Yeah. Well, and again, I mean, that's light years ahead of the big room size freezers that you mentioned. And it does remind me, again, it reminds me of this original evolutionary path of computers, right? I mean, the first mainframes were these room size computers. And again, people were using punch cards on them, and they couldn't imagine at the time, they couldn't imagine something, even like you mentioned, that would fit in the palm of your hand, and so the fact that you're visualizing that now, I mean, Lord only knows, give this a few more years and it'll be in a really remarkable place.
What will your phone look like in 10 years? Right? I mean, it's only been 15 since we've had iPhones. What possibly is it going to do? What's the size factor? I don't know.
Yeah, yeah. Well, so, another aspect of this, and this is giant, and this is right up your alley, is quantum programming languages. And what I'm seeing is the emergence of Python, which you wrote a book about, as well as Qiskit, Ocean, Q Sharp, Circ, and I believe there are a couple of other languages out
Yeah.
there. So which of these do you think is currently the best language? And does it seem like this emerging industry is starting to standardize on a language yet, or is it still kind of a free for all?
Well, there are always a lot of programming languages floating around. And if we were to look at general computing, we would have to throw in Java, JavaScript, C++, ECMAScript, Rust, Go. There are dozens, and then it's a favorite pastime of many people to invent some little language. So in fact, if you go to Wikipedia, you can probably find dozens and dozens of so-called quantum languages. But here's really the key thing, though, is let's start with Python. So last time I looked, the estimate was there were about 8 million Python programmers. Do you build a brand new quantum programming language with completely different syntax, which has to fit into all the tools that you use, the editors and everything like this, just because it needs to be quantum, right? Or do you build it as a set of Python libraries? So stick with what you know, but extend it just in the same way that people have created thousands of Python libraries through the years. And that's the direction that Qiskit has taken, as well as Circ. Those are Python libraries. So Python is the programming language. Those
Ah, okay.
Q Sharp is its own flavor of a language. It's similar to C Sharp, which is, and they're both pretty much Microsoft things. There's a little open source thrown in there. And then there's like lots of people who said, yeah, I'm going to invent my own language and things like this. We had this discussion back in the early days of IBM Quantum, which programming language to use and what would be the strategy. And we decided to go just building on Python. It's a great choice. It's proven to be a very good decision. Just as I did in the Dancing with Python book, teach them what they need to know and then extend that, build on it. The other problem too is, if I said I'm going to create Bob's new quantum programming language, I gotta actually support the language. I'm going to spend full time just working on the language and not doing any quantum stuff, because making programming languages is hard, and supporting it with compilers and things like this. And I will forget what I originally wanted to do. So build on the best, the most modern languages and extend them. Don't create something brand new. And that's Qiskit and Circ, which are the big two, really, in that order.
Oh, okay. Qiskit and Circ, and that's good to know. The reason I asked is it reminds me almost when you talk about building on existing languages. Years ago, I worked at a company that used Tandem Guardian systems, and they had the TAL language, if I remember right, Tandem Advanced Language. So we had a room of Unix programmers, standard Unix programmers, who for them, they'd come in and doing their coding was just part of their daily routine, right? They'd sit down their Solaris workstations and just get everything done. The Tandem guys would have these big discussions about the actual language. And, at the time, I mean, the number of programmers who could write this language so spread out that if they ran into a bug, it might take them days, sometimes weeks, to get an answer, right? Either from the manufacturer or from their peers in other parts of the world. So, it's definitely a stumbling block unless you have something, again, this goes back to the infrastructure that's in place that people can build on.
Custom languages. I will say it's a lot of fun creating a programming language for the first 3 weeks. And then you get a lot of annoying things, and you get users and, as you said, bugs and things like this. In many ways, the 80s were the heydays of lots of different programming languages. We were still early enough in the history of computing that people were trying out different ideas, object-oriented, C++, Smalltalk. When Java came in, it was seen as being pretty much, maybe this is the last language. Maybe this is going to solve all the problems. Well, people eventually realize it didn't, right? It does some things extremely well. And then you started seeing about 15 years ago, people experimenting yet again, because now we know about the web, right? And different types of programming, and the whole programming models start changing. So we've seen a resurgence of people playing with programming languages, but it doesn't take very long to figure out what's the top 10 and why, really.
Yeah, yeah. Well, now let me change tack and talk a little bit about hardware, because again, it looks like IBM is using circuit-based computers and cryogenically cooled chips, and the packaging on this new Osprey chip, this thing looks really conventional. I mean, it looks like it just plugs into a regular board. I was really amazed when I saw a photo of it online. Will we see quantum computers begin to enter data centers soon with relatively traditional packaging? And you know, I realize the cooling systems do change this a fair amount, but you know,
So, yeah, it's, I'm sorry to interrupt you, but yeah, and let's just remember in the fullness, because I'm trying to be expansive across the industry in my remarks. Google is also working on superconducting. Amazon Web Services has a big effort. Rigetti, there are quite a few other smaller companies doing some superconducting. And yes, they do require quite a bit of refrigeration. They need cooling down close to absolute zero. And
yeah,
once you get that cold, right, there are certain thresholds in cooling where you have to change the technology. So liquid nitrogen will get you so cold, nitrogen plus liquid helium will get you so cold, and things like this. So what starts to happen is that the cooling, the volume of the cooling apparatus starts to dominate. And yeah, they'll get a little smaller, and we'll get smarter about doing it. So those you have to think of taking up a chunk of real estate in the data centers. That's right. For a lot of the other types of technologies, you know, as I described before, when they need cooling, it will be more supplemental cooling. They can operate, some of them can operate at room temperature up to a certain size, and then to really get the control, the fine control in a pure enough vacuum, you're going to need a little bit of cooling. So if I had to guess, there'll be a class of systems that will live in data centers. These will be the quantum supercomputers. Who cares how much room they take up? We have plenty of room. It's unknown what their energy requirements will be, though. You know, even if they compute something faster, how much energy will they use to actually do that? It can be hard to estimate. So there'll be that class. The second class is computing at the edge. And so for the edge, I want you to imagine a cell phone tower. And, you know, if you look kind of carefully down toward the bottom of the cell phone tower, there's often this little concrete block room, and that's where the equipment is. And people are thinking about computing at the edge. Well, what would it mean if I could put a little quantum computer and, you know, maybe 1 meter by 1 meter by 1 meter. So it's not tiny, but it's not that big. I'll stick in the corner of your little room. I start thinking, what can I do with quantum computing at the edge? Some of the AI applications we talked about before. People are very interested in distributed or federated machine learning. You can't bring everything back into the data center. How might quantum play in that space? If I have sensors of different types that are living out at the edge. Now here, maybe the edge isn't a cell phone tower, maybe it's a plane or a submarine or a ship, right? Again, a cube about 1 meter on a side isn't so bad. And then the next generation will be, for certain types of technologies, maybe it's rack mounted, right?
okay.
So think of this in kind of cycles of 5 to 10 years each, right? And they'll overlap a little bit. So we're first going to worry about, oh, who cares how much room we have? Next 5 to 10 years. And then we'll worry about computing at the edge with quantum. It's a great target, though, right? We understand the data center. Maybe it's smarter to aim for the edge, the next generation, right? And then the generation beyond that. So, as I said, the next 15 to 30 years, you'll see all of these, I think.
So it'll shrink down, just as we've seen with normal computers. Now, ColdQuanta, your firm makes sensors. That's you don't just make quantum computers, you make that as well as sensors and other quantum technologies. Do you think that we'll see those end up in IoT and Internet of Things? I mean, will they shrink as well? Will sensors ever be small enough? Because I realize they don't take as much bulk, I guess, as a quantum computer itself does.
Yes, they will. And the atomic clocks, I mean, just to call out something in particular, um, these radio frequency receivers. So just, I'm not obsessed with cell phone towers, but nevertheless, you go and you look at a cell phone tower, look up toward the top, and you'll see different things that look like horns. You'll see different large boxes. Um, the sizes of those things actually relate to the frequencies, the wavelengths of what they're trying to pick up. Well, quantum doesn't have these types of correlations. So if I built a radio frequency receiver, it would be the same size for one frequency as it would for another, which means in the same amount of space, potentially I could receive signals at lots of different frequencies. This has commercial as well as, you might imagine, military uses as well. One great application already, aboard the International Space Station, there's something called the Cold Atom Laboratory. And at the core of that is ColdQuanta technology. So they're experimenting with cold atoms on the space station in space. So, speaking very much from a company pride perspective, if you say, well, how robust is your system? Well, we stuck it on a rocket and shot into space and it still works. So yeah, very much, right? And then the form factor and the exact use may vary, but there's an application already. So it's a space Internet of Things.
Yeah.
Internet of Space Things. I don't know what the right acronym is.
Well, so let me switch gears just a little bit and ask about one of the things that I've seen in the news is that quantum computing it could be dangerous for current cryptography, especially in terms of online financial and crypto transactions or breaking potentially sensitive communications. Do you think that quantum resistant algorithms will be enough to safeguard these systems? Or do you think that quantum computing will render traditional cryptography completely obsolete?
So let's describe the problem, first of all, because I don't think most people think about crypto. I don't mean cryptocurrency, though it's related in some sense. If you make a purchase on the web, your information, your credit card information is encrypted. So it's rendered into a form that someone just kind of in the middle, if they were peeking, they probably couldn't figure out what it was. But by the time it actually gets to either the retailer or the bank on the other side, they can decrypt it. So you have a key on one side to transform it into what looks like gibberish. And on the other side, there's another key that takes the gibberish and actually brings it back to information like this. Well, where do these keys come from? Well, certain schemes come from extremely large numbers. And they take what are called prime numbers. So for those of you who don't remember from high school, numbers like 2 and 3 and 7 and 11 are prime numbers. You can't break them down into products of smaller numbers, except with one. But a number like 12 is 2 times 2 times 3. All right. So what you do is you get these really large prime numbers and you multiply them together and you get another really big number. And that very large number is used in and is related to these keys. Well, it turns out that for some very big numbers, it's extremely hard to factor them. If I could take that product and break it into the 2 smaller ones, I could say, here's one key, here's another key, right? With a little bit of work, right? And things like this. So how hard is it to break that big number into these 2 smaller numbers? If it's easy, then you don't have a great crypto system. If it takes 1 million years to do the factorization, You say, I can live with that. If no one can break this in a million years, I can. Okay, 1995. So in fact, quite a while ago, right? Peter Shor, then a researcher at Bell Labs, now a professor at MIT, came up with an algorithm that could factor numbers almost exponentially faster than what we know how to do today. Now, this word exponentially, I want to clarify a little bit. A lot of people use this like, wow, that's exponential growth. And all they really mean is that's really fast. Well, sorry, we got to go back to math, exponents, actual real exponents and things like this. Let's say something took 1,000,000 seconds. Now, 1,000,000 is 10 to the 6th power. 6 is the exponent. So if you can do it in 1,000,000 seconds, 10 to the 6th, if I can do it exponentially faster, I can do it in 6 seconds. You see, I grab that exponent, and that's the new time. There's a big difference in doing something in 1,000,000 seconds, 10 to the 6th, and doing something in 6 seconds.
Yeah.
But if this algorithm says we can do it in that 6 instead of the 10 to the 6th. And so now people start to get scared. This is not an imminent threat. We need, the last estimate that I saw is around 20 million qubits to break current encryption. And as you mentioned at different times, the largest chip right now is IBM with a little bit more than 400. 20 million, 400. So nobody's going to be breaking, getting your credit card next Tuesday using a quantum computer. But we do have to worry about two things. First thing is, what if somebody stole data now? And you might say, well, somebody would steal your financial information or your health information or our company's information. And they're going to decrypt this in 10 or 15 or 20 or 30 years. And using the eventual, maybe if we get them, quantum computers. That's a problem. Steal now, decrypt later is the problem. And you might say, look, I really don't care in 15 years if somebody looks at my healthcare information. I'm annoyed, but maybe it's not a problem. What if these were launch codes? There's a lot of information that hangs out for a long time that maybe you don't want someone to see in 5 or 10 or 15 or 20 or 30 years. So what you'd better do is move from any of the encryption schemes you have today that are vulnerable to this being able to factor problem or similar problems. There's variations on what the problem is. To what you refer to, so-called post-quantum encryption methods. And these are methods, to the best of our knowledge, you cannot use a quantum computer to crack. That it's just quantum computers are not, they don't work on every type of problem, right? They're not good for every type of problem. And so the idea is find out a form of encryption where quantum computers have no special advantage in actually breaking that encryption. So the National Institute of Standards and Technology, NIST, ran a 6-year program. They have now published several different schemes that you can use. They're working on standardizing this. Sometimes with some institutions like banks, I've heard that it can take a bank 10 years to completely overhaul the encryption methods. So start moving away from the classical methods that maybe someday will break and really look at this as a cybersecurity problem. It's not so much a quantum problem, but from a cybersecurity perspective, if you're not using the latest technology and you're leaving yourself open to attacks, well, shame on you, whether it's quantum or otherwise, right? So that's where we are on that.
Absolutely. Robert, let me thank you again so much for your time today. And let me close by asking, what comes next for you in your career, and what should we look for in the near-term headlines in terms of quantum technology?
So for me, I'm fascinated by ColdQuanta. It's a great company. In this down market, we just announced a few weeks ago that we got $110 million Series B investment. So, and this is very much based not just on our doing quantum computing, but all these other quantum technologies. There was a great Wall Street Journal that said how we were focusing on the here and now as it related to quantum technologies. So there's so much to do there, and I'm having a blast and wonderful people. I am working on a second edition of Dancing with Qubits. I started the last one about 4 years ago, and it's shocking how I need to touch it up here and there. I think for the headlines this year, I do think we're going to start hearing more and more about this quantum interconnect issue. And I think, and I hope we're going to start getting many more practical headlines associated with quantum security. Pragmatically, what should people be doing instead of silly things that talk about the quantum apocalypse? Let's get people the real details and a real plan to work with this instead of just trying to scare them.
Wonderful. Sir, thank you again so much for your time today.
Great to talk to you, Tim. Thank you.